Yes.
You're able to access that, okay?
Yes, we are.
Okay, excellent. Very good. Well, welcome back. Nice to see you all, to see some of you and see the names of others of you. So, last lecture, the first lecture, so let me share my screen here. Okay, so we started last lecture with this basic family, right? F of x equals ax plus b. We looked at it quite systematically. I don't know if you've had time to think about it a little bit more. Does anyone have any questions about this before we move on? This is the first basic set of examples. Okay, I think you should be able to, pretty much describe everything you see here. So today we're going to do something hopefully that you will find interesting. So we're going to continue with a very similar class of maps, except that we're just going to make one small modification, which is going to have a very significant impact. And this is the following. So this is a map on R, right? And now we're going to take a similar map but we're going to take mod 1. Do you know what that means, mod 1?
Yes, Rigidu.
So we are taking non-integer part, I think.
Exactly, the non-integer part of the number.
Yes.
Right? So that means that this is really a map. So this means that when you take 0, 1, this means that all our numbers are between 0 and 1 because they're the non-integer part, right? So if you apply the map, if you take a number between 0 and 1, x0, and if x1 lands outside, then you translate it back to the non-integer part of x1. So this now, when we take mod 1, this becomes a map from 0, 1 to itself, because we always take a number between 0 and 1. And in fact, 0 and 1 are identified, right? Because mod 1 is 0. They're the same point. So this is sometimes useful to think of this mod 1 as a map of the circle. I'm not sure if you have ever seen, maybe in the topology course, this notation here. The quotient space. Circle is the quotient space. This is exactly the same thing as taking mod 1. So the quotient space means that you identify all the points that are whose difference is an integer, and that means that you're just taking exactly the fractional part of the point. Okay, so we're going to study a family of maps S1, S1, and we're going to start with the case A equals 0. So we're going to start by taking in particular this case here, f of x equals x plus b. So let's think first how that changes when we're on the real line and when we're on the circle, right? So if we're on the real line, you remember this was one of the examples we looked at. So we just take x0 and then we add b, right? x1, x2, x3, x4, and so on. We just shift by b each time, right? So we have that xn is equal to x naught plus nb. And what happens now when we take mod 1? When we take mod 1, if you stay inside between 0 and 1, it does not make any difference, right? So x naught goes to x1, goes to x2. But then when you go to x3, this is bigger than 1, and so you need to shift it back to its decimal part, its non-integer part here. So this is exactly, you can imagine this as a map of the circle where we have, now it depends on what orientation we want to use, it doesn't matter. So this is x naught, and then suppose this is b, x1 equals x naught plus b, and then we just add b. So in this case, it's much bigger, so we take many more iterates, or I am thinking of b is smaller, and then when you come back around, you just start again on the other side, so you keep rotating. So I don't expect you to immediately see what the dynamics is, because that's what we're going to study. And as we shall see, it's quite interesting. It can be quite interesting what happens here. So again, we're going to start by trying a few examples. So what is, so when b equals 0, we already know what happens, right? What happens when b equals 0 in this case? So this would be mod 1. We're going to study this mod 1.
Every point is fixed.
Exactly. So this is exactly the same as when we looked at the map on the real line. It's just f of x equals x. This is the identity map. Every point is fixed. What other b shall we try? What is a kind of simple example?
For any natural number, again, it is fixed.
Exactly. That's a good observation, Junaid. So if we take b equals k in n, then again, this is just f of x equals x plus k mod 1, and this is just equal to x. So because you're just going round and round every time. Okay. So let's take some b between 0 and 1. For example, let's take b equals 1/2. F of x.
All orbits periodic. In general, if b is rational number, then all orbits will be a periodic orbit.
Okay, let's see. Let's work towards that. So Mimokshin is saying that if b is a rational number, then every point is periodic. Let's just try one or two examples, and then we will try to write down the general formula, right? So what happens when b equals 1/2? We have x naught, then we have x1 equals 1/2. Sorry, equals sorry, this is x plus 1/2 mod 1. So we have x naught, and then we have x1 equals x naught plus 1/2. Excuse me just 1 second. So here I am. And then we have x2 is equal to x1 plus 1/2, which is equal to x naught plus 1/2 plus 1/2, which is equal to x naught plus 1, which is equal to x naught. Right? So this is very simple. So if you think of it on the circle has length 1 because we're identifying 0 and 1. So this is x0. x1 will be exactly on the other side. We will go halfway around, and then we will come back. X0 is a fixed point for f2. Is that okay for everyone? Okay, so maybe we can go a little bit more quickly. It's easy to see if b equals 1/3, what's going to happen? The same thing, right? So x naught, and then you will go by 1/3. Here x1 is equal x naught plus 1/3, and then we'll go around to x2, which is equal to x naught plus 2/3, and then it will go back to x0. So every point will be periodic of period 3. Right? So we can easily generalize this, as Mirmukshin was saying. So for example, if b is equal to 1/q, where q is some natural numbers, then f n of x naught, so xn is fn of x naught, is equal to x plus nb mod 1, which is equal to x plus n/q mod 1. So if n is equal to q, then this means that xq is equal to x plus q/q mod 1, which is equal to x naught. Right? So every point is periodic. So if we have x naught here and we translate by 1/q, x1, x2, and so on, each of these distances is 1/q. So when we apply this q times, we will come back exactly to x naught. What happens if we take 2/3?
Three times.
Sorry?
Period
You still need 3 times.
3.
because
Will it still be periodic of period 3?
Mhm.
Yes.
Yes.
Exactly, except that it will go down twice in some sense, right? So if it is 2/3, then you start with x naught, then it will go all the way to here. x1 is x naught plus 2/3, and then it will go around again to 2/3 to here. This will be x2 is equal to x1 plus 4/3, and then we will add another 2/3, and we will have x3, which is equal to x1 plus 6/3, which is equal to x1 plus 2, which is equal to x1 mod 1. Okay, so now we can quickly generalize. We can see that if you have, as Mirmukshin said, if you have any rational number p/q, where p and q are integers, then we have fn of x is equal to x plus n p/q mod 1, because that's all we're doing. We're just adding p/q n times, and therefore if n equals q, we have fq of x equals, oops, what's happened here? Can you still see my screen?
No.
No? Okay. Okay.
Yes.
fq of x equals x plus q times p/q equals x plus p mod 1. This is equal to x naught.
Professor, do P and Q has to be relatively prime?
Good question. What happens if they're not relatively prime? So what happens if we write f of x equals x plus 3/6.
Get period 2.
Exactly. So by this calculation, of course, we will show that they are period 6. I mean, because it's got 6 on the denominator, you have f of 6. X equals x plus 6, 3/6, which is equal to x plus 3 mod 1, which is equal to x. But as we discussed last time, this you have to be careful because this is not the minimal period, right? So it will still be of period 6, but of course these are not, it's a fake period 6 because actually it's period 2. But if it's period 2, then it's also period 4, it's period 6, and so on. So if P and Q, as you said correctly, Ling, if P and Q are, if the fraction P and Q is reduced to its minimal terms, then Q will be the minimal period of all the points. Is that okay with everyone? So we have this proposition that if beta is rational, then it implies that every point is periodic. Of the same period, right? Of the same period. It's kind of a generalization of the identity map in some sense. It's basically saying that some method of the map is the identity map, right? Because every point is periodic of the same period, so some period is the identity map in this case. Okay, so what if beta B is irrational?
Then all orbits is dense.
And Mokshim, I really appreciate your contribution, but what can you argue it? Can you explain?
For proving this statement, we consider the function in the half-open interval. It's just one proof. Maybe there are other proofs. And is this function, we can show that it's Lipschitz continuous. It's analytical proof. And alpha is beta B is irrational number. Then we have n plus m beta. All of them, m plus n beta. M, both of m and n integers. Then fractional part of these numbers is equals to m beta, and we can show that any subring of R, if it is not isomorph to Z, then it is dense in R. We use this fact to proving all orbits is dense.
Okay, that is correct. That is one proof. So we're going to use a slightly different argument that is self-contained. It does not use any theorems from algebra, from anything, okay? But so Mokshin is right. So what we're going to show is that proposition. So if beta is not rational, then we have a very interesting property, which is that every orbit is dense in S1. So what does dense mean? Do you remember from topology what that means? We can't hear you, Junaid. I can't hear you. I think you're mute, maybe. Or...
The closure of the orbit is S1.
Exactly. The closure of the orbit, right? So let's see. I'm not sure if I introduced the omega limit. I'm sorry. There will be some moments because I'm now teaching two very similar courses at the same time. I'm teaching a version of this course with a group of students in Pakistan, and I'm teaching a version of this course now here. So sometimes I cannot remember exactly what I went through here and what I went through then. So I'm not sure if I defined the omega limit set of the orbit. I think not, right?
Oh,
Yes.
No.
So let's just go through that to introduce a little bit of terminology, which is very important, okay? So if you remember, the forward orbit of a point is equal to the sequence xn. This is an infinite sequence, right? And when you have an infinite sequence, a natural question is, what are the limit points of this sequence, right? So the limit points of the sequence are all the points that are to which you have a subsequence that converges to that point. Okay, so I will not go through, I'm sure you're all familiar. If you don't remember so much about sequences, subsequences, limits, you should review that. But let me just say that we have that the omega limit set of x naught is by definition equals to all the limit points of this orbit. And this is more precisely equal to all the points y in our space X. This is in a general metric space, such that we can find the subsequence of the orbit which converges to y as nj converges to infinity. This is a very important definition because it really allows us to describe the asymptotic properties of non-periodic orbits. Right? If an orbit is periodic, then in principle we can describe it precisely. A periodic orbit is a finite set of points. So that's the orbit. Okay. If the orbit is infinite, there's many different things that this orbit may do. As we saw in the last class, for example, if f of x equals 1/2 of x, then this orbit will just converge to 0 at the origin, right? And then what is the omega limit of this point? So for example, in f of x equals 1/2 of x that we saw before, right? So we have 0, we have x naught, x1, and so on. What is the omega limit of x naught in this case?
0.
Exactly. It's just the single point 0, right? Because in this case, we have that the orbit actually converges to 0. So this is a converging sequence, and a converging sequence has a unique limit point. That's the definition of a converging sequence, right? But in general, a sequence might not be convergent, and it might have many subsequences that converge to different limits, and therefore it may have many limit points, which is the definition of omega limit, is the set of all the possible limit points. So what we're going to show here precisely is that every orbit is dense is a bit like saying that the omega limit set of every orbit is equal to all of S1. It means that every point on the circle is a limit point of the sequence. This is really quite remarkable, actually. I mean, Mokshin is right, he's correct in identifying the result, and his argument for the proof is correct. We will try to look at a little bit more. I will leave some parts of it as an exercise. I will not give the full proof here because you can work through it, but I will try to give some idea and some of the steps, right? So first of all, what is the image that we should have in our mind of what that means, right? So what are we trying to show? This is the circle. This is some arbitrary point x naught. And then we have the orbit of x naught is just going round and round the circle. And what does it mean that every point on the circle is a limit point of x naught? This is what we want to show, right? To say that omega x naught equals S1 means that every point z in S1 is a limit point of the orbit. So now I take a point z here. What does it mean that it's a limit point?
It's every neighborhood intersects the orbit of x naught.
Exactly, right? So I take a neighborhood here, U. It can be, for example, z minus epsilon, z plus epsilon. Take a very small neighborhood. I'm drawing it big. And what I'm claiming is that if I wait long enough, at some point, I will find some point xn1 of the orbit in there. So the orbit cannot jump always across this neighborhood. Even if I take the neighborhood very small, right? Because if I take the neighborhood very small, you may imagine that I jump, so x1 is equal x naught plus b, and then I jump by b, and then I jump. So every step I'm jumping quite a bit, and then I say, okay, I jump across this neighborhood, and then I keep going, and then I keep going, and maybe every time I come close, I jump it. And I'm saying, no, it's impossible to jump across it. This is what we need to show, right? That for every point z and every epsilon, some point of the orbit falls inside there.
What is the natural phenomenon having this kind of behavior?
Excuse me?
What is the natural phenomenon having this kind of behavior?
Ah, that's a very good question. You mean in the physical world?
Yes.
In the physical world, the physical world is not as exciting as the mathematical world, right? No, so this kind of phenomena is, let's see if I can think of some situation that might be somehow related to this. I think this kind of dynamical system can be used in the context of planetary orbits which rotate. And so let's see, I'm just kind of making up here, right? Making it up. I don't know. I don't have an immediate answer for that. But in some sense, you could, this kind of question is a little bit similar to this other question. Suppose you have two orbits that rotate around the sun with different periods, right? So will the relative position of these orbits, is it periodic? Will it, the Earth goes around the sun in 365 days, and then the Mars goes around the sun in I don't know how many days, right? Then a natural question is, if they start at the same time, right, and then one of them finishes this orbit and the other one does in the other orbit, will it be some time after which they will be both back exactly at the same starting point in the same starting position? So will this configuration be periodic, or will it be forever out of synchronization in some sense? Okay, this is not exactly this, but it is related to this kind of problem.
Okay.
Okay, I don't have a more precise question for a physical phenomena that does this. But in mathematics, this turns out to be a very important phenomena that occurs in many situations, actually. And I will give you today a very nice application of this result to a problem which is completely outside dynamical systems. In the second part of the class, I'll give you a very nice application of this to number theory. Okay, so how do we show that this happens? How do we show that the orbit of x naught intersects every single arc of the circle? Because basically that's what we're saying, right? We're saying that because we need to be able to show this for every z. So we need to show that for every z and for every neighborhood of z, the orbit of x naught intersects this neighborhood. So this is the same thing as saying that the orbit of x naught intersects every arc, however small, of the circle, right? So this is a little bit like saying that, suppose we can show that, if we can show that for all epsilon greater than 0, the orbit of x naught intersects every arc of size epsilon, then we're done, right? So you take epsilon very small. So in other words, we can do this. Suppose we fix epsilon, and then we cover the circle with arcs of size epsilon. Okay, this is epsilon. They do not need to be disjoint, but we just cover with a finite number of arcs of size epsilon. And suppose we can show, let's show that the orbit of x naught intersects every arc that I have just drawn. So if I can do this for every epsilon, then I'm done, because I have shown that I can approximate every single number, right? So I take, however small I take epsilon, I divide the circle into a finite number of arcs of size epsilon, and I show that the orbit intersects every single one of these arcs, and then I'm done. I'm okay. So let's do that, right? So we fix epsilon. And now we're going to show that the orbit intersects every single arc. And then because epsilon was arbitrary, if we can do it for one epsilon, we can do it for any epsilon. And then we have shown the proposition. So how do we do that? We have x naught is here. How big is b relative to epsilon? So how should we visualize this situation, right? Because we have now x1 here, say x1 is equal to x naught plus b. So how shall we visualize this? Shall we think of b being big compared to epsilon, small compared to epsilon?
If epsilon is small,
What is the correct picture? Should I draw it like this, or should I write x1 here? Is it a small translation, small rotation, or big rotation?
We can just show that on 0 it's gonna be like only on 0 it's gonna converge something. It's smaller than each epsilon, and then you just add all the epsilons and you will end up in each interval.
Yeah, I think you're in the right direction, Yunus. You're in the right direction, but you were not precise enough. What do you mean? So
yeah, I mean that only one point is sufficient. Like if we have only like one point is a limit point, and that is true by compacity if it's not periodic. Then.
okay, that is a good conjecture. Let's try to understand exactly what you mean. So yeah, Eunice, can you be a little bit more step by step? Take us through one step at a time.
So we want each interval of length epsilon to have points in it from the orbit to intersect the orbit.
That's what we need to show. That's right.
Yeah. So now imagine that the orbit contains a point smaller than epsilon.
What do you mean by contains a point smaller than epsilon?
I mean, the distance between that point and 0 is smaller than epsilon.
Try to be more precise. Yes.
We said this is R mod 1.
Yes. Okay. So we
So
take
we want
0.
it to be smaller than epsilon. It makes sense.
So how can we show? So what you're saying is, suppose I know what you're saying, and it's exactly the right direction. So what you're saying is that suppose that we can find okay, so this is 0, and you're saying suppose that we can find a point inside the same arc that contains 0. Is this what you're saying?
Yeah.
Okay.
If that arc is less than epsilon, then and there is a point in it, then each arc of epsilon has a multiple of that point.
And why is that?
It's because otherwise it's gonna take a leap bigger than epsilon, and this is contradictory.
Yeah, you need to be a little bit more. You need to explain a little bit better. So let's Yunus, what you're saying is exactly in the right direction, but let's go back a little bit. So how can we show that this orbit of x0, that there exists at least an arc, one arc? So I have divided the circle into a finite number of arcs. I am now looking at the orbit of x0.
Hello?
hello, can you hear? I can't hear.
What is that?
I'm sorry, this was my internet connection for some reason. I had problems with my internet connection. Let's hope that it will be okay. So let's go back to the screen. Okay. Okay, sorry about that. Okay, so we are moving in the right direction. So we have we would like to first show, so step 1, let's say, show that there exists one arc with at least 2 points of the orbit. I think this is what, Eunice, you were really thinking of. I'm not sure that you can fix 0 to begin with, but what we really need is just one arc with 2 points.
Yeah, by compacity and not periodicity.
That's right. So can you be more precise about that? What information are we using here to show
So
that?
we use that it's not periodic. So
And therefore,
there is an infinity of points.
and therefore,
But this S1 is compact, so there must be a limit point.
exactly. Okay. So there must be a limit point. So I keep having problems here. Are you seeing my screen now?
No.
Oh, no.
No,
I don't understand why it keeps cutting out. That's right. So there's 2 ways to see this. Okay. One option is exactly what Eunice is saying. So the orbit of x0 is not periodic, which means it's an infinite sequence. S1 is compact, and therefore there must exist a converging subsequence. This is what you meant, Eunice, right?
yes,
And therefore there must exist some limit point. Okay, and so if there exists one limit point, it means there are points of the orbit that are arbitrarily close to that limit point. Okay, another way to see exactly the same thing is just that the first part is the same. Okay, so we have the orbit is infinite and there exists a finite number of arcs. So this is sometimes called people refer sometimes this to the pigeonhole principles, right? If you have n boxes and you have n plus 1 elements, and you put them all in the boxes, some box must have at least 2 elements. Right? In this case, we have an infinite number of points. We only have a finite number of arcs. Even if epsilon is very small, you have 2 million arcs, but it's still a finite number. So there must be one arc that contains at least 2 points. Okay, but the conclusion of both of these is that there exists at least 2 points. And why is that interesting? Why is that useful? Because that means that if this is x naught, we have here.
I'm sorry, Professor. Can I explain again the pigeonhole principle? The pigeonhole.
The pigeonhole principle says that if you have a n boxes and you have n plus 1 objects, and you want to distribute n plus 1 objects in n boxes, you must put 2 in the same box.
But
isn't
that is for discrete case?
Excuse me?
Isn't that is for discrete case?
This is a discrete situation, right? So this is a infinite. So you're right. So the key point is that because the orbit of x naught is not periodic, then it is an infinite sequence. So it contains an infinite number of points. And here we have a finite number of arcs. So we have divided the circle into a finite number of arcs. And each point belongs to one of these arcs.
But the arc is the interval of the arc is not discrete, right?
No, but imagine that you just index these arcs. Suppose you have 1 million arcs, right? Every point of the orbit belongs to at least one of these arcs. So you cannot have just 1 point in every arc, because if you had only 1 point in every arc, the arcs are the boxes, right? These intervals. So you divide the circle into a finite number of intervals. Then we have an infinite number of points, which we want to distribute in these arcs. So there must be at least one arc that has to, I'm not saying yet that every arc contains a point. That's the second step, right? So this first step is just that there must be at least one arc that contains 2 points.
Okay.
One arc that contains 2 points. In fact, I mean, what Yunus said is more, we only need this, but of course, the argument of Yunus' argument shows that there must be one arc with an infinite number of points, which is also obvious, right? Because we have an infinite number of points. They're distributed inside a finite number of arcs. So there must be one arc that contains an infinite number of points, right? But for the moment, we're just interested in the fact that there exists at least 2 points. So here there's a point xn, and here there's a point xm, and they're inside one arc of size epsilon. We agree with that?
Yes.
Yes? Okay. So remember that both xn and xm are in the orbit of x naught, right? So xn is equal to fn of x naught, and xm is equal to fm of x naught, right? So, and I think this again is, Yunus, what you were saying before, right? Is once we have this, we're okay, because how do you go? So n and m will not be equal. This would be obvious, right? So it's either n bigger than m or m bigger than n. It doesn't matter. So let's suppose n is bigger than m, just to simplify things. Okay, this means that we're going from x0 to xm to xm, to xn, right? So here we have fn, here we have, here we have fm, here we have fn, and here How many iterates of the map do we need to go from xm to xn?
N minus M.
Exactly, n minus m, right? So we have that f n minus m of xm equals xn. Is that okay? So what does that mean? That means, again, we have x naught here, we have xm here, and we have xn here, and this distance here is less than epsilon, right? And we have that f n minus m of xm is equal to xn. So what can you tell me about f n minus m of xn? Where will that be in the circle? Can it be here? So this is x of 2n minus m, right? Where will this be, this point? So
Moves by something smaller than epsilon.
that's right. So this is the key point of the whole. So pay attention here, because this is the key point of the whole argument is this. Okay, so I realize it's not completely trivial here, but what we're saying is that if you take the fn minus m iterates, remember that when we looked at the rational case, I said that, fq is the identity, right? So if you take a rational rotation, 1 over 100, for example, then when you go around, you iterate 100 times, you come back exactly where you started from, okay? So what this is saying is that when you iterate n minus m times, you come back almost exactly where you started from. Almost. You come back here within epsilon, right? So f n minus m of xm minus xm is less than epsilon. Because this is equal to xn. So this means that this iteration n minus m is basically a rotation by a small number, even though n minus m might be big. So you're actually maybe going around many times, and you're taking very high iterate. The effect of translating n minus m times the original rotation is the same as having a rotation which is less than epsilon. So when you apply this again to xn, you will get another point here, which is also less than epsilon from xn. In other words, f n minus m is of the form g of x equals x plus, let's say, c mod 1 for some c less than epsilon. This. And then we're done, right? Because then this means that then if we take iterates f, k, n minus m of x0, right? K is an integer, then we will intersect every arc of size epsilon. Because you're taking iterate. So Fn minus m is a small translation of size less than epsilon, and then you apply it again and again and again. And so here you start with x0, and then now the original translation was b, x0 plus b, but now if you apply Fn plus m, sorry, n minus m, and minus m to x0, then you will land very close by less than epsilon. And then you will land again very close, very close, very close. So you're now, every step you're taking is smaller than epsilon. And then, of course, you cannot jump over any of these little epsilon arcs. And so you must intersect every arc. Oops. And so you must intersect every arc. Okay, so both the arguments that Milmukshin gave and Yunus, you had exactly the right idea. And this conclusion is that every point is a limit point. Okay, so if you know, of course, as with all the things, you need to just think about this a little bit, go through all the steps, make sure you understand all the steps. I put it as an exercise also in the question sheet with some steps, and I think you should be able to follow the argument without any problem. So you see, Mohsin, that this argument is more self-contained. You do not need to use, your argument was correct about the subgroups and so on, but in this argument is much more direct. It doesn't need any big theorem to use this. Okay, so this shows that every, for the map f of x equals x plus b mod 1, we have two cases, be rational, in which every point is periodic, and be irrational, in which every point is dense in the orbit. So these are two quite remarkable behavior that we got just by adding mod 1. As Yunus said, it's basically because of the compactness of S1, we get much more interesting phenomena. Okay. Okay, so let's take a little break now. Let's take a 10-minute break so you can just kind of relax a little bit, have a glass of water, and then I will give a very nice application of this result. Okay? So I will see you back in 10 minutes, exactly. Okay? So... Okay, welcome back, everyone. So, okay, let's share again. Okay, so I want to give you now a little application that I think is really quite amazing. I hope you will be amazed. Even though we've done very little so far already, these results have some, we can show some things that are really not obvious. And maybe this will satisfy Ling that has some, we have some kind of natural, I don't know if this will count as natural phenomenon or not. But the question is the following. Suppose you take the sequence 2 to the n. So this is a sequence of numbers, right? So this is just 1, 2, 4, 8, 16, 32, and so on. You know this sequence very well. So my question is, can we say anything about the blocks of digits that occur in this sequence? So for example, if I choose just some arbitrary digits, so if I let P be some number, whatever number, like 35,821. My question is, does there exist n in n such that 2 to the n begins with P, 35821? If there is, can I do this for any number? So you give me any number you want. Does there exist some n such that 2 to the n begins with this number?
What do you mean by begin?
Begins, exactly. Ling, that is a very good question. What do I mean by begins? Because this is part of understanding, of finding a solution, is to understand very precisely the question, right? So what I mean is that I can write 2 to the n to be equal to 35821 and then some other digits. So if this is, let me write this as A0, A1, A2, A3, A4, and then A5, A6, up to some wait, let me just check. I want to make sure I use the notation which I'm going to use.
35821 is odd number, right?
Excuse me?
The P is odd number, right?
It does not, well, this is the question. The question is, can I always find some numbers for any number you gave me? So suppose so this would be A5, A6, up to AN, right? So 2 to the n will be a number, and the first 5 digits of this number will be the number that you give me.
Oh, okay.
That's what I mean. What do you think? Does it sound reasonable? Does it sound possible, or does it sound completely crazy, impossible that this may happen, that I can actually find any number, even if I choose a number with 1,000 digits, I can find some 2 to the n that starts exactly with those 1,000 digits, and then it has some more digits afterwards. And if it's true, what does it have to do with dynamical systems? And what does it have to do with circle rotations?
Dividing by residue is, I think, main idea is.
Excuse me?
Dividing by residue, namely we consider, for example, mod 1 million or something. Then connection with previous problem is that dividing by residue. Consider residues, mod something.
Mod what? So you're right now that you're looking for some connection, and somehow what we did before is we looked at some recurrent something that had to do with mod 1. So let me state maybe let me actually state the result properly that we're going to prove. Proposition. So let k be an integer, k bigger than 2, and k not a power of 10. Because of course, so let me write it, not a power of 10. Then for any p in n, any natural number p, there exists n greater than or equal to 1 such that k to the n begins with the digits of p. Right, so like we said before, so kn, so if p, let me be clear, so suppose we write p is equal to a0 to al, okay, then there exists n, so I'm just trying to write it better, there exists n such that 2 to the n, k to the n is equal to a0 to al plus 1 to am. Is the statement clear? What we would like to show?
Yes, it is clear.
Okay. So why do we have to exclude the powers of 10?
Because these are always 1, 0, 0, 0, 0.
Exactly. So this clearly cannot work for powers of 10. So the remarkable thing is that it works for any other power. Okay. In some sense, what this means is as you take powers of k, you kind of go through all possible combinations of digits in some way. So how can we even approach this problem? As Milmukshin says, some kind of residues or some kind of mods. That's right. So how can we write this? I think it's really not easy at all to arrive at some idea until you see it. So let me try to give some suggestions here. So this is what we want to show. So this number here is really, what does this number here mean? This number here, what does A0, AL, AL plus 1, AM is really saying that we can write this as A0 to AL, AL times 10 to the M plus AL plus 1 to AM. Right, because that's what this means. The fact that we have M terms here means that this is really equal to A0 to AL 0, 0, 0, 0.
10 to M minus L. If A0 is the first digit, then
I'm sorry, you're right, Milmokshan, thank you. What I wanted to write here is L plus M, just to make it easier. Yes, thank you very much. So this is M terms. So this is M, and this is plus AL plus 1 to AM. So our original number P is equal to A0 to AL. So what we're saying is that we can write K to the N is equal to P times 10 to the M plus Q for some Q less than 10 to the M.
we can divide, for example, 10 to
This is what we need to show. Sorry, this is what we need to show. We need to show. So if we can show this, we're done, right? Because if we can show this, then that's it. That's what this means. That's what this is exactly the same thing as what we had here, which is exactly the same thing as the statement, right? What this means, if we can write K to the N as some P to the 10 to the power M for some M plus Q, where Q is less than 10 to the M, then that's exactly, we've shown what we want to show, because this means that you can write it like this, that you can write K to the N. Sorry, so this was supposed to be L to the M here. Okay. So the question is, can we do that? We've reduced, what we've done now is we've reduced the problem to showing this, because this is exactly the same thing. So we have reformulated the problem, right? So this is the initial stage of the problem solving. We have reformulated the problem in a different way, which we hope might give us some clues as to how to do this. I really, this particular calculation is not, this particular argument is not something that I think is easy to figure out on your own. So that's why I'm really giving you the steps. But notice that this is equivalent to saying what? This is equivalent to saying that K to the N is greater than or equal to P 10 to the M, P plus 1, 10 to the M. So the exact value of Q is not important. We just want to be, what we are interested in is the value of P, because P is the number that we fixed, right? And all we're interested is that we can write K to the N as P times 10 to the M for some M. We also don't care what M is. And we also don't care what Q is, right? M and Q are two numbers. As long as we can find M and Q, so we can write it like this, then we have solved that problem. We don't care what M and Q are. And in fact, Q, we particularly don't care about, because as long as we can write Kn, as long as we can show that there exists some M, so as long as we can show that there exists some M such that Kn is between P to the 10M and P plus 1 to the 10M, then that's fine, right? Because that means that we can write Kn as P times 10 to the M plus some number Q, which is less than 10 to the M. Junaid, is that okay?
Yes.
Toluwane,
Yes, it is.
you're okay? So what we've shown is a series of equivalent steps, right? So we started with the statement of the proposition and shown that the statement of the proposition is equivalent to this. It's just saying, if we can find an M, if we can show that there exists an M such that Kn, so what we're given is P, right? K and P is what we're given. So if we can show that there exists N, there exists M and N, such that this is true, then we would be fine, right? Because if this is true, that means that we can write Kn as P 10 to the M plus Q, which means we can write it exactly like this. K to the N has, our P in it, and then it has some other digits, which gives the Q. So this is now what we have to show, is this. And now we're starting to go in the right direction. So now, what do we do with this? Well, we want to show that there exists M and there exists N. So we have Kn squeezed into these two. So we have 10 to the M on both sides. So kind of an interesting possibility would be to take logs of this inequality, log base 10. So this is equivalent to saying that there exists M and N such that log base 10 of P10 to the M is less than or equal to log base 10 of Kn, which is less than log base 10 of P plus 1, 10 to the M. And now when we take log base 10, what does this mean? So this is log base 10 of P plus M log base 10 of 10 less than or equal to N log base 10 of K less than or equal to log base 10 of P plus 1 plus M log base 10 of 10. Okay, this I just did. I just took the logs and I multiplied them out. And what do we have here? So log base 10 of 10 is just 1. Right, so log base 10 of 10 is just 1. So we can really write this as log base 10, 10 of P plus M less than or equal to N log base 10 of K less than or equal to log base 10 of P plus 1 plus M. And this, you can see, is, so we've got M on both sides, right? So we can subtract M from everything. So this gives log base 10 of P less than or equal to N log base 10 of K minus M less than log base 10 of P plus 1. Okay, these are a few technical steps, but they're just algebra, really. This is what we have arrived at. Okay, we want to show that there exists M, N, such that this holds. Now, notice that this central part is squeezed between these two terms, right? Log base 10 of P plus 1 and log base 10 of P. So if we're going to show this, it might be useful to know how big this range is, right? So we're saying that this here, how tight are our conditions, right? So in other words, what is log base 10 of p plus 1 minus log base 10 of p? How big is that? Can you see how big? Is this a big interval? Do we have a lot of space to play with? Or do we have a very tight interval to play with?
Right.
So this we can write, this is the difference of logs. So we can write log 10 of p plus 1 over p.
Asymptotically equal to 1 over p.
Sorry?
Asymptotically equal to 1 over p with some coefficients. 1 over p.
Well, asymptotically, it goes to 1, right? So p plus 1 over p, yes.
Zero. The length of this interval asymptotically is 0.
Yes.
1 over p is its speed of convergence.
So when p is very big, this is very close to 1. This is very close to 1. And the log, therefore, of that is very close to 0. Does this make sense? So this makes sense, right? Because remember that p is our number that we start with. If we take b very big, if we take p with 1,000 digits, you will expect it to be very difficult to find, to satisfy the statement of the proposition, right? But still, this is positive, right? Also, what is the biggest possible number that this can be? So what is the smallest value of p that it can be? P is the number that we chose from the beginning.
P could be 1.
P equal to 1. Yeah. So when p equal to 1, so this is monotone, the log, right? Log of p plus 1 over p, and p plus 1 over p is monotonically decreasing in p. So this is positive, but this is always less than or equal to log base 10 of 2. When p is equal to 1, this is 2. And it's easy to see that this log base 10 of 2 is less than 1. So this means that even for any p, the gap here between log base 10 of p and log base 10 of p1 is less than 1. Okay, so this means that we want this distance here, n log base 10 of k minus, has it disappeared again?
Yes.
Yeah.
I don't understand why this happens. It keeps disappearing. So this means that we're looking for some values of n and m, where n log base 10 of k minus m is very small, in particular less than 1. But we can choose any m we want. Okay, so of course, n, which m are we going to choose? If you fix n log base 10 of k, which integer are we going to choose to make this as small as possible?
Could you please repeat the question?
So you have n, we want this to be as small as possible, right? In particular, we want this to be less than 1.
Infimum is 0.
Sorry?
Infimum is 0. If m and n is any natural numbers, then it can be converged to 0.
Well, that's what we have to show. That's what we have to show, right? So what I'm saying now is fix n for the moment. Okay. And then we write n log base 10 of k. And now we want to choose an integer m such that this minus m is the smallest possible. Positive number, smallest possible. Because this has to be positive. So what are we going to choose for m?
As large as possible.
As large as possible, but less than n log base 10 of k. So what is the largest possible integer which is smaller than n log base 10 of k?
Floor function. The floor of n log 10k.
Sorry,
Integer
let's say
part.
again.
Integer part. So
The
this
integer part.
after this one is
The floor
fraction.
function.
The integer part. Right? So clearly, if you look at this here, this m, so what this means is that this is the same thing as saying there exists n such that log base 10 of p is less than or equal to n log base 10 of k mod 1 less than or equal to log base 10 of p plus 1. These two things are equivalent.
Connected.
Oh, sorry, we lost it again. I really need to understand why this is happening all the time. I don't understand. So you see writing that n, there exists m and n such that n log base 10 of k minus m is squeezed between the two numbers is the same thing as saying n log base 10 of k mod 1 is squeezed between these two numbers. Because we are subtracting m, but we can choose m whatever we want. So we take m, the integer part, and then that just means that it's n log base 10 of k. Okay, so now we are 95% of the way there, right? So we need to show that there exists n such that n log base 10 of k mod 1 belongs to the interval log base 10 of p log base 10 of p plus 1. I don't believe it. I will try to understand why this is happening all the time. So this is the chain of implications, right? So now, how do we prove this? Oh my gosh.
It's orbit of 0.
Exactly,
Yeah, b is that logarithm, that irrational number.
Exactly. Very good. So this is just, as you say, the orbit of 0. So we let b equals log, sorry. B equals log base 10 of K, right? And then this is just N log base 10 of K is just equal to Fn of 0 under this map, where F of X equals X plus B mod 1, which is just the maps that we had before. So this is the orbit of 0, N log 10K. And so the question is, does the orbit of 0, does there exist N such that Fn of 0 belongs to this interval log base 10 of P, log base 10 of P plus 1. So all we need to show is that log base 10 of K is irrational. This is always true if this is true, if log base 10 of K is irrational. Oh my God. There really has to be some reason why this is going on. Okay, and the fact that this is irrational is I mean, we can easily check it. So suppose by contradiction, so suppose log base 10 of K equals, let me not use P over Q here because I'm used here. Let's say is L over M, where Lm are integers. Okay, then this is equivalent to saying that M log base 10 of K equals L, right? And this is equivalent to saying that log base 10 of K to the M equals L, and this is equivalent to saying that K, we take exponentials, K to the M equals 10 to the L. Okay, and this can only be true if K is a power of 10. Right, so this is by contradiction. If we suppose that it is that log base 10 of K is rational, it must be a power of 10. Since we assumed it's not a power of 10, it's irrational. Okay, so this implies that log base 10 of K is not rational.
Professor, can I say something now?
Yes.
In our previous previous inequality in above, please. It's inequality, double inequality. No, above again.
This one here?
No, above again. It's just this one. This one. Now we come here that our problem. Namely, there is a subring of R. This our. I am talking about this double inequalities. If we permit n and m is any integers, then this one is ring. Yeah, it's isomorphic to z square, z2 to z square, and this one is a ring, subring of R. Then this inequality is proving that this subring is dense in R.
Yes, that's correct, Mokshan, yes.
So we can prove this statement, this claim, by using via another approach, namely using algebraic methods. Namely, any subring of R that is not isomorphic to Z, then it must be dense in Z.
Sure, that is absolutely right. So it's very good, Mokshan, to make these connections. You're right. There are these connections between, the algebra. So this is showing how connected all these results are, right? So you're right. If you know that result, then it follows. But I think sometimes it's nicer to be able just to give a direct proof that does not use any more sophisticated mathematics, right? So it is a good observation to connect these two things, but using that means bringing in some more heavy mathematics, whereas here we have given a completely direct proof that does not use any theorem from anywhere, right? It is completely self-contained. So sometimes it's better, if possible, to give just completely direct self-contained proof.
Yes.
Okay, so that's it for today. I wanted to, we did the circle rotations. We did this nice application to number theory. We will also see other applications to number theory. I think it's very intriguing how dynamical systems often has this, as I said, it's quite interdisciplinary. It has lots of connections with different parts of mathematics. So, wait, let me stop sharing here so I can see you better. So what I would like to kind of discuss with you maybe sometime next week is about how this, this is the first time I'm giving these lectures in a very different way from the way I usually give them. Usually I give them on the board. Perhaps you've seen some of the lectures on YouTube from the previous years. So I don't know how it is for you. My idea was that because we have to do it on Zoom anyway, so doing it with a tablet would give us more opportunity to have more interaction, to discuss as we have been doing. There are many different ways we could continue. We could I could in fact give the lectures on the blackboard in the Budinich like the other professors do, or we can continue exactly in this way as we're doing. Or another option to make it even more interactive, which might be interesting, is that you read the lecture notes in advance, because I have lecture notes with all this stuff, and then we discuss. We have a real discussion about the lecture notes instead of me presenting the result, which anyway is in the next lecture notes. Or another option is that you take turns and one or two of you, for example, present each class, you present some section from the lecture notes in which we discuss. So I think this new system, is an opportunity for us to explore different ways of learning and teaching and to find out what is best for you. So why don't you think about it a little bit, okay? And then we can next week, either next week on Tuesday or on Thursday, we can discuss and maybe we can try different options. If this works for you, I realize that maybe one of the things that might not be so good is that my handwriting is not perfect. I know that. And because we're having this discussion, I have this tendency to write maybe a little bit more in a way that's a little bit more messy than what I would do if I was on the board, writing carefully on the board. I don't know if this is a problem for you or not. So anyway, I'm just presenting the idea that next week we can discuss, and if we want to try some different methods that you think might work better for you, then we can do that. Okay, so just think about it, talk about it within yourselves, and I'm very open to exploring different possibilities. Okay, so okay, so you have already the lecture notes that contain all this stuff. Have a look at that. You have the exercises, so try to do that and let me know if you have any questions. And we will schedule, I think, for Wednesday, the first tutorial. So on Wednesday, you can see the tutor and you can discuss more in detail these things.
Is it next Wednesday?
Excuse me,
starting-
Link?
Is this starting from next Wednesday?
Yes. This next week, Wednesday. Today's Thursday, right? So the next possible Wednesday on the 3rd, I think is the 3rd of March.
Okay.
Okay. I will make sure we put it in the, I will talk to Patrizia and we'll put it in the schedule. Also, by the way, we might have to change, I will talk to Patrizia, so we might have to change the times of, because there's a few administrative meetings at ICTP that I have to go in and they clash with some of our lectures. So I will send you a message to tell you, but probably by today or tomorrow, Patrizia will have changed some of the classes, okay? So she will make sure that they're not clashing with other classes, but there might need to be a few changes with the timetable. Sorry about that. Okay, have a good weekend, everyone.
Thank you.
Okay,
Thank you.
okay, bye.